Thank you for joining us for our presentation on token-based conjoint, a new framework for too-many attributes. First, let's set the stage on how we got here. We had a client come to us and say, I want to know which combination of benefits will make people buy my product. So we hear the word combination and we're thinking conjoint analysis. So we ask our client, well, how many benefits do you want to test? But then they tell us they want to test 30, maybe even up to 40 benefits. And that makes things a little difficult because we know that traditional conjoint methods are going to struggle when there are that many binary attributes. And respondents are going to struggle with trying to consume so much information changing on every screen. In our toolbox today, we have MaxDiff and conjoint, but MaxDiff, while great at getting a stack rank for the benefits, the results are not additive or combinatorial. So we cannot simulate how one might feel about a combination of benefits, just if one prefers benefit 1 over benefit 2. We can resolve that problem with conjoint and measure those additive effects, but traditional conjoint breaks down when we have a lot of attributes. Not to mention, traditional design generation algorithms are going to try to balance on the number of times each benefit is seen. So if you build a design, you're likely to see a lot of concepts or alternatives with the same amount of benefits turned on, right? Maybe you'll have 3 alternatives per screen and they'll each have somewhere between 7 to 9 benefits turned on. Instead of what I think we want, which is a balanced number of combinations of just 1 benefit turned on, 2 benefits turned on, 3 benefits turned on, and so on. Our solution to this problem is what we're calling token-based conjoint, or TBC. In a TBC, we'll be able to simplify the choice for the respondent and ultimately have better predictive power because we're able to capture diminishing returns. So let's take a look at what the TBC would actually look like for a respondent. Here, you can see a screenshot on the right of the exercise. Respondents see a subset of benefits. In this example, we're showing 7 per screen, but you could toggle with this setting. And we'll call this number N. We ask them to select their top K preferences, and we do this dynamically using a constructed list. N stays constant on every screen, but K can vary. And then, after they make their selections, there's a dual response question that follows. And spoiler alert, so far the signal shows that this supports 40 benefits, far more than CBC. Here's just another screen so you can see how the N stays the same at 7, and the K changes from 4 to 2 to 5, etc. And the dual response is going to remain fixed as well. Now, let's just take a second to call out that to capture the same amount of information as a 7 choose 2 TBC task using a standard CBC, we'd have to show all possible combinations of N choose K on one screen. That's 21 concepts, as you're seeing here. And of course, we would trust the respondent to read all 21 concepts and choose the one they liked best. And in a 7 choose 4 task, we'd have 35 concepts and have to ask the respondent to do the same. Kind of gross, right? So just from a UX perspective, TBC seems pretty valuable so far. And it's actually pretty easy to execute. It's a standard MaxDiff design, and then you set up a free format question that references that design, and you use a constructed list for piping in the number of items, or K, you want them to select per screen. If you're still intrigued by the end of this and want to try it out, we've put an SSI template on GitHub so you can create your own TBC exercise. In our design, we have a systematic approach to randomly selecting between that 1 to 6 for our K out of our 7 N, which always stays fixed. All right, so let's assume we've fielded the study and collected our data. The next question is, how do we actually model this? Let's start with a simple example for one task that shows 5 items and is asking you to choose 2. So our N is 5 and our K is 2, and in this scenario, the respondent picks items 2 and 4 from the set of 5. We then want to code this one task as follows. Our first step is to exhaust all the possible combinations of N choose K. So here, 5 items choose 2 equals 10 total pairs, if we're thinking MaxDiff CBC designs. We want to put the winning combination first, for no other reason than this will make sense later. And then we'll sort the remaining pairs by if they have a winning item included in them or not. And again, for no other reason than you'll understand later. So you see the first 4 alternatives include the winning item number 2, and the next 3 alternatives include the winning item number 4. And the last 3 alternatives do not include either item 2 or item 4. We also need to address how we're going to code and add the information captured in that dual response. Because we're numerically curious at Numerius, we ask the dual response on a 5-point scale, which gives us the flexibility to explore a top box coding, a top 2 box coding, and a calibrated coding of the none, where we assume if you say you definitely would subscribe, then you're probably 70% likely to subscribe. And if you said you probably would subscribe, you're probably 30% likely to subscribe. For what it's worth, we like this flexibility in case we need to tune the model to get closer to actuals. And we use the calibrated information in the standard logit rule formula, so not too surprising, right? The exponent just changes based on how you are coding the none. The downside is that a calibrated model can't be done in our current on-the-shelf tools that we have today. Something else to consider, just for fun, is how we also code the none. So Sawtooth's approach to coding the dual response none comes from Diener et al. In 2006, where if a respondent says they would buy the product, the information is just captured in that single task. But if a respondent says they would not buy the product, the information is going to be captured in 2 tasks. The first task is going to include all the alternatives and which one was chosen, and the second task is going to include all the alternatives and the none, where the none is going to be chosen. But again, numerically curious, we thought, why not revisit this and ask ourselves, why do we have more information for some tasks, but not others? Hear me out. For a 12-task dual response conjoint, one respondent could have just 12 tasks, and another respondent could have 24. The latter respondent saying they would not buy anything across the 12 screens, so they have 2 tasks to represent every screen. The former respondent saying they would buy everything, so they only have 1 task to represent every screen. So we said, let's go ahead and try another version of the none, where every respondent has 2 tasks to represent each conjoint screen. And we're going to call this the naive none. Here you can see us attaching task 2 to represent the none. This task, again, will be attached to every task in the naive none, whether or not they choose the none, but only added if the none is selected in the Diener none coding. So if we double click a little bit more into the detail on that added task with the none across the different modeling alternatives, for the top box model, we would add the first set of rows if the respondent picked the top box, and the second set of rows if the respondent did not pick the top box. If we're using the Diener coding, remember we would never add the first set of rows. For the top 2 box model, it is exactly the same. We would add the first set of rows if the respondent picked the top 2 box, and the second set of rows if the respondent did not pick the top 2 box. Again, if we're using the Diener coding, we would never add the first set of rows. The calibrated model is slightly different. Because it's calibrated, it's impossible to do the Diener approach, and we have 3 separate ways of coding for the 3 separate categories. If you selected top box, we're saying you have a 70% likelihood of purchase, and 1 minus 70% equals 30% goes to the none. For the second box, we said you had a 30% likelihood of purchasing, and the inverse of that is the 0.7 that goes to the none. And then if you're not in the top 2 box, which ends up being the same coding as the top box and the top 2 box coding for when you select the none, 100% probability.
All right, now that we've laid out how the exercise works, let's dive into some real-world data. We'll examine 3 blinded client projects. This will help see how the approach works with different audiences and in different contexts. But to keep it engaging for you, we'll pretend that each of these projects was a fake subscription meal plan called Quick Bites. And on this slide, I also want to note that we had different sample sizes for each project and different number of items. This is a screenshot of what that fake meal kit would look like as a fixed task. Here we're showing 4 different benefits you would receive by subscribing and asking all respondents to state whether they would subscribe or not. We included 2 of these tasks in each of the projects. These holdouts were the same for every respondent. This approach allows us to measure how well the model can predict these tasks and provides like a benchmark for evaluating predictive performance. So how do we validate our model's performance? We use 2 approaches. First, we perform an in-sample validation. This means we run the model on the entire data set and see how well it predicts those 2 tasks that everyone saw. Next, we move to a more generalizable test, a 4-fold cross-validation. We split the respondents into 4 groups. For each fold, we hold 1 group out, train the model on the remaining 3 groups, then test it on the held out group. This process gives us a clearer picture of how well the model generalizes to new respondents who weren't part of the original study. Here we're comparing 3 different ways of handling the dual response none across the 3 different projects. And we've summarized the results using 2 tables, one showing in-sample validation and the other showing out-of-sample validation. It's really important to interpret these tables correctly. Don't read them top to bottom. That would be comparing different projects, which is like apples to oranges. Instead, read the rows left to right. Each row represents the same data set, so that is an apples to apples comparison. We're looking to see which none coding produces the lowest mean absolute error on the types of scenarios we want to use for reporting here. And in all cases, it appears the naive none is lower, which gives us confidence to move forward with this coding for our reporting. So far, we've focused on mean absolute errors to gauge how well our model predicts purchase likelihood for a single subscription scenario. This gives us a good measure of whether someone would subscribe, but it doesn't tell us how well our model can rank different subscription options. To gain this deeper insight, we need to look at likelihoods across the random choice sets presented to the respondents, because we didn't include this type of scenario as a fixed task. This will help us understand not just if people would subscribe, but which features or bundles are more attractive. Essentially, likelihoods give us a richer picture of how well the model can rank options beyond the yes or no scenario. So let's talk about what we mean by likelihood in this context. Likelihood answers a fundamental question: how probable is the observed data given a set of parameters? In frequentist methods, we often try to maximize this measure. Essentially, it's a robust metric that helps us understand how well the model can predict the observed choices. By looking at likelihoods, we're able to assess not just whether the model can predict a single outcome, but how well it can rank multiple options across different choice sets. This gives us a much richer understanding of how well our model performs in more scenarios. Also, all of our models have the same number of parameters, so we don't need to take that into account by adjusting the likelihood into a different measure. Now let's dive into how we validated our model using a hold one out strategy. Each project includes between 12 and 14 tasks, with each task representing a different screen of subscription options for respondents. To validate the model, we hold one task out at a time. We estimate the model parameters using the remaining tasks, and then we use those parameters to calculate the likelihood for the held out task that was unseen by the model. By repeating this for each task and summing the results, we get an overall measure of how well the model explains the data it hasn't seen. So here we're comparing the likelihoods across 2 different scenarios. The first table shows how well the model performs when ranking subscription options that didn't include the none option. Here we see that the naive none and the sawtooth none approaches are essentially comparable. This tells us that both coding methods provide similar predictive ability when it comes to ranking subscriptions. The second table looks at likelihoods when comparing a single subscription to the none option, similar to how we want to report this. As we saw with the mean absolute errors, the naive none approach outperforms the sawtooth none in this scenario. This is expected because the naive none model was specifically tuned to handle these types of choice sets, so it's no surprise that it performs better in this context.
So, what have we learned so far? Well, the biggest aha is that this works. We've also learned that the naive none, in this case, is better than the Diener coding, so we'll move forward with that. And we like the 70-30 calibration, so we'll also move forward with that when we present our results to the client. So here you can see an example of what those results would look like. First, we can simulate every individual benefit versus the none and create a stack rank of all the benefits tested. For simplicity, we're just showing a subset of the top 5, middle 5, and bottom 5 options, but we would have this information for all the items tested in the TBC. This output would be similar to reporting the probability of choice max diff results, where it's a likelihood out of 100%, or a one concept versus the none in a conjoint simulation. In our opinion, best of both worlds, max diff like output, but conjoint like value, particularly when we get to the next deliverable, which is the simulator tool. So since we had simulations of one benefit versus the none, and the goal was to build the optimal bundle, we can create a simulator tool to dynamically see how the take rates change as more benefits are added. And because we have individual level utilities behind the data, we can look at the results at the total level or by subgroup. The highlights you are seeing are dynamic, and we're showing what the next best benefit is after you've added something to the bundle. And the numbers dynamically update. This simulator template is also available on GitHub if you're interested in trying to replicate it and see the backend math. We can then chart the increase in likelihood to purchase as each additional benefit is added. This example here just uses a greedy approach, always adding the next benefit that increases the overall probability of subscribing. And you can see that in our data, the first benefit really drives up subscription likelihood. Then from there, there's not a huge bump in take rate as additional benefits are added, which we may or may not expect depending on the feature set we test, the value of the initial feature. And of course, you could have multiple versions of this chart depending on how you choose which benefits to add next.
At this point, we're feeling confident about the results we've achieved. The methodology worked well for the different projects, but this naturally leads us to ask, how scalable is this approach? What if we wanted to test subscriptions with more than 40 items? Could we scale up to 60 items or more? What if the subscriptions involved larger bundles, 10, 20 items at a time? Can this exercise scale? As we consider scaling up, we face a significant challenge, the exponential increase in combinations. So for example, if we ask the respondent to choose 2 items out of 5, that's 10 combinations. If we ask them to choose 10 out of 15, we're looking at over 3,000 combinations. This exponential growth means that the number of alternatives in each choice set can quickly become impractical. The model could take too long to run, or the probabilities might become so small that we run into numerical precision issues. So the question becomes, can we smartly tailor these choice sets to preserve the signal that we need while avoiding these limitations? We need to explore ways to simplify the choice architecture without losing the meaningful insights that come from the data. To explore the scalability challenge, we're introducing a new option called Option 2A. The idea is to start with the original choice set, which includes all the n choose k combinations. Then we augment this with additional choice sets, one for each of the winning k items. In these additional choice sets, we compare each winning item against all the items that weren't selected. So for example, if the original task was to pick 2 items out of 5, the original choice set has all the combinations of 5 choose 2. That would be task 1 here on the screen. But we also add 2 more choice sets, one where the first chosen item is compared against the remaining items, and another where the second chosen item is compared similarly. While option 2A helps by adding simpler comparison tasks, we're still including the original n choose k choice sets. But what if the set becomes too big? We could run into problems. That's where option 2B comes in. In this approach, we drop the original n choose k choice set entirely. Instead, we rely solely on the augmented choice sets, where each chosen item is compared against the items that weren't selected. The hope here is that we avoid the explosion of combinations, but keep enough comparisons to be informative. Now let's shift our perspective. While the option 2 series focused on adding additional tasks to improve the model, the option 3 series will explore the opposite approach. What if we take things away? In this series, we examine how we can streamline the choice set by removing alternatives that may not be as important. The goal is to reduce the complexity while still capturing the critical information needed for the model. What we're calling option 3A tried to trim the fat from the choice set by removing all alternatives that only include items that weren't chosen. In other words, we keep only alternatives that contain at least one item from the winning set. For example, in a 5 choose 2 scenario, there are combinations that consist solely of items that weren't picked. By removing these, the model no longer considers these less relevant items. Now, this could be a bad idea. The model might lose out on information about these less preferred items. While option 3A offers a simple way to simplify the choice set, it doesn't scale when k approaches n because there's actually nothing to remove. So we introduce option 3B here. Instead of keeping one large choice set, we break it down into smaller chunks. For each winning item, we create a separate choice set that includes all alternatives containing that specific item. In this example of 5 choose 2, we end up with 2 smaller choice sets, one for all alternatives that include the first chosen item, and another for all alternatives that included the second chosen item. This chunking approach makes the model more scalable. Instead of dealing with one massive choice set, the model processes smaller, more focused sets. Now that we've explored the different ways to simplify and scale our choice sets, it's time to see how well these approaches actually perform. In the next section, we'll dive into the results of our scalability tests. We'll look at how each of these options, whether adding, trimming, or chunking, impact the model's performance. Now let's look at the mean absolute error results from our different choice set options. We have 2 tables here, one for the in-sample validation and one for the out-of-sample validation. Each table shows the performance of our baseline, option 1, with the naive none, and the 4 new options we tested. What we see is quite revealing. Option 3 performs relatively well, suggesting that trimming non-winning combinations might not harm the model after all. However, options 2A, 2B, 3B perform poorly. This indicates that our modifications somehow undermined the model's ability to predict accurately. So what could be going wrong here? Why did adding these synthetic choices hurt the model so much? In the following slides, we'll dig deeper into the reasons why we think it might have hurt. One reason why the models might be doing worse is that we are adding more individual level data without more information. Now you might ask, why would more data be a bad thing? Not all data is the same. Our new data is just a repackaging of the other data, but the model's math doesn't take that into account. In a hierarchical Bayesian model, the posterior distribution is a combination of the prior and the likelihood. This creates a dynamic called adaptive shrinkage, where individual level estimates are pulled towards the sample mean. When we have more information about an individual, the model will shrink them less, potentially leading to the model being overfit. Another issue is that each screen has a different number of choices. Should the choice on a 3 choose 5 screen be 3 times as important as the choice on a 1 choose 5? Probably not. We probably want to treat them all the same. So if adding synthetic choice sets led to less adaptive shrinkage and poorer model performance, is there anything we can do about it? One potential solution is to weight the likelihood contributions of these additional choice sets. Instead of treating each synthetic choice set as fully independent data, we can downweight their impact. In other words, we can change the math so that all the choice sets per screen only have the weight of one choice set. This approach helps maintain the model's appropriate level of uncertainty, ensuring that we don't lose the benefits of adaptive shrinkage. Let's take a look at what happens when we apply the weighting strategy to the synthetic choices. Here we see the in-sample validation results. The new weighting options show a dramatic improvement. They have some of the lowest MAEs across the board. indicating that this approach not only fixes the shrinkage issues, but potentially boosts the model's predictive performance. Here we see the out-of-sample results. Again, the weighted options outperform the raw version and often surpass the baseline. This shows that by smartly weighting the contributions, we can harness the benefits of synthetic choices without compromising the model's performance. So the takeaway is clear. When we control for the overconfidence in individual level data, adding synthetic choices can enhance our model's predictive accuracy. Before we get too far ahead of ourselves, it's important to remember that we've only looked at MAEs so far, comparing one subscription to the none. We also care about being able to rank different subscriptions. So let's revisit the likelihood-based validation. We'll use the same hold one task out approach, running the model on the remaining tasks, checking how well the estimated parameters justify the data in the held out task. This will help us confirm whether the improvements we're seeing in the MAEs also translate to better performance in terms of rankings and overall likelihoods of the observed choices. First, we'll look at choices without the none option. Here the goal is purely to predict which subscription options are preferred. We see that the unweighted synthetic choice options 2A, 2B, 3B perform worse than the baseline and other options. That's consistent with the MAE results. However, the weighted versions, along with the original options, are all comparable. This means that breaking the choice sets into smaller components doesn't degrade the model's ability to correctly rank the options. In fact, it may even enhance its predictive abilities. Next, let's look at the likelihood results for the scenarios that include the none option, essentially measuring purchase likelihood. Here we see the weighted options perform exceptionally well. Option 2B is the row max in each case. This shows that breaking the choice sets into smaller weighted components not only preserves, but actually enhances the model's ability to predict purchase likelihood. The unweighted versions, on the other hand, perform much worse, confirming that the weighting approach is critical. Bringing it all together by combining the results from the previous two slides, what we see is a consistent signal. The weighted options continue to outperform their unweighted counterparts and even match or exceed the baseline. This consistency across both MAEs and likelihoods gives us confidence that these custom ways of creating the choice sets do not hurt the model. In fact, they potentially improve its performance. This suggests that we can consider scaling up our experiment by chunking the choice sets and applying appropriate weighting. This way we retain the signal and improve the model's performance without losing valuable information as we scale the exercise.
All right, so our final, what did we learn? Well, TBC appears to be a very viable approach for measuring combinatorial preferences for long lists of benefits, features, items, and much easier for the respondent than those traditional approaches. More exploration around the naive none is necessary, though, as it seemed to do very well given this use case and our fixed tasks, but we would love more folks to test it and try it out. And of course, whenever we are adding more data to the model than we theoretically captured, those synthetic choices, we need to remember to weight our information so the model continues to use the strengths of Bayesian probability. A couple of drawbacks, though, that need to be mentioned. We're never showing a 2-benefit alternative against a 3-benefit alternative in the experiment, right? Everything is being compared to the none threshold. So just keep that in mind when you think about choosing a TBC. And while the design is easy, if you want that weighted likelihood model that we showed you, then you're going to need custom models outside of the standard tools that are available today. So with all that being said, what are some of the next steps? Well, we'd love for you to go to the Numerius GitHub and download the SSI and simulator tool so you can start using TBC today. We saw that weighting helped, so why not apply that in every study we do with the Diener none coding, or just use the naive none coding. And this is just one, well, technically 3 studies, but more research is always needed to verify the reproducibility of our results. So we welcome any and all additional efforts in this space. And we would love to help support you in your first TBC. Please email us with requests for how we can do that best. Perhaps it's creating a web portal where you could upload your inputs and we could spit out the outputs for the model, or potentially even run the model for you. Or maybe it's a Python or R package if you're keen to execute it on your own. Or maybe it's a request for a Lighthouse Studio build, in which case you should probably email Brian. But we don't want this to be the first and last time you see TBC. Help us help you bring TBC to your projects. And thank you so much for listening.